Hello everyone, I'm Jordan Xiang from UIUC, and I'm happy to present our brief announcement paper called Optimal Good-case Latency for Byzantine Agreement, Broadcast, and State Machine Replication at Disk. This is joint work with Itai Abraham from VMware Research, Kartik Nair from Duke University, and Ling Ren from UIUC. Our work is motivated by permissioned blockchain systems where state machine replication protocols are essential building blocks for constructing such systems. Most of the existing SMR solutions are leader-based and contains two components, one steady-state protocol and one view change protocol. The steady-state protocol can drive consensus decisions very fast under a good leader, and when the leader is malicious and not following the protocol, a view change will be triggered to replace the leader. But the view change is usually costly and slow. In practice, the overall performance of SMR largely depends on the performance of the steady-state protocol, which can make progress efficiently with good leaders and good networking conditions. This also motivates this work to further investigate the performance, such as latency, of Byzantine fault-tolerant protocols under the good case. We believe the good case latency is an important metric to study for BFT protocols such as SMR. The traditional literature mostly focuses on the worst case latency of BFT protocols, which is the latency to terminate in the worst case on the F Byzantine faults. It is well known that in the worst case, any BA or BB protocol cannot finish faster than F+1 rounds. If the actual number of faults is less than F, which we denote as T, the protocol still needs to run at least T+2 rounds. But the above worst case scenarios do not capture the common good case where the protocol may finish much faster with a good leader like in SMR. So we define and study the notion of good case latency, where the network and local computations are fast, and the leader is honest for SMR, or the sender is honest for Byzantine broadcast, or all the honest parties have the same input for Byzantine agreement. The same input definition in Byzantine agreement is motivated by SMR. Since the leader is honest in SMR, then all the honest will receive the same input. We want to find a family of protocols that optimize the good case latency so they can be very efficient in practice. In this paper, we consider the synchronous settings, and we adopt a more refined latency characterization from the literature. We assume the message delays are upper bounded by small delta, which is unknown, but there is a pessimistic upper bound big delta, which is known to the protocol designer, and usually the big delta is much larger than the small delta to ensure the safety of the protocol. We will characterize good case latency in terms of both small delta and big delta, and we assume small delta is very small compared to big delta, since the network is fast under good case. Other settings are quite standard. We assume the communication channels to be reliable, authenticated, and all-to-all. Our protocols will use PKI and standard digital signatures. This table summarizes previous results and our contributions. The good case latency is initially studied in sync-hot-stop, while SMR protocol with good case latency 2 big delta plus 1 small delta is proposed, with a lower bound of 1 big delta for Byzantine agreement and broadcast. Our paper further reduces the good case latency to 1 big delta plus 2 small delta for both BA, BB, and SMR. Our protocols are optimal if we neglect the small delta, as the small delta is much smaller than the pessimistic big delta. Now, as an example, we describe our broadcast protocol called 1 delta BB. Here we assume the number of parties is 2F plus 1, and up to f of them can be Byzantine votes. Initially, the broadcaster proposed a value b to all the parties P1 to Pn. After receiving the proposal from the broadcaster, the party first forwards the proposal to all other parties. At the same time, they start a timer of duration 1 big delta. If no equivocation of the broadcaster is detected during this 1 big delta period, then the party will send a vote message on the broadcaster's proposal B. The equivocation may be detected either by receiving different proposals from the broadcaster directly or by the proposals forwarded by other parties. Next, if the party receives f+1 vote messages on the same value B, it will first forward the vote messages to all other parties, and then set a local value log to be this value B. So if the time of receiving these messages are within 3 big delta, they will commit the value B right away. Finally, at time 4 big delta, all the parties will run a BA protocol with its local value log as input. And any party who have not committed yet will commit the output of the BA. Now let's see why this protocol has good-case latency 1 big delta plus 2 small delta. In the good case, the broadcaster is honest. It will broadcast the same value to all the parties, and it will only propose one value. Also, all the messages are signed, so the Byzantine party cannot create fake proposals signed by the broadcaster or any other honest parties. Therefore, during the 1 big delta waiting period, no equivocation will be detected at any honest party, so they will send vote messages for the broadcaster's value B, and after 1 small delta, f+1 votes can be gathered at all honest parties, and they will commit the value B at time 1 big delta plus 2 small delta. Now let's see why this protocol is correct, which means it ensures agreement even if the broadcaster is malicious. First, if all honest parties commit at the last step of the protocol after the BA, then by the agreement of the BA, they will commit the same value. Otherwise, if some honest party commit a value B by receiving f+1 votes at the earlier step, and there is no other value B prime committed at the same step, all the honest party will receive the f+1 votes messages forwarded within time 4 big delta, and therefore set log to be value B. So all the honest will input value B to the BA at the last step and agree on the value B. We show that the above cases are the only possible cases, and there cannot be two sets of f+1 votes for different values B and B prime. Suppose if they are, then each of the set must contain at least one vote from the honest party. Without loss of generality, let's say the vote for B is earlier than the vote for B prime. Then the proposal B forwarded by the honest party who vote for B will reach the second honest party before its timer expires, and therefore the second honest party will not vote for B prime since it detects equivocation. So this is a contradiction, and therefore no two different values can both get f+1 votes. Here is a summary of our presentation. Our paper argues that the good-case latency is an important metric for BFT protocols in practice. And our paper proposes a family of BFT protocols that are simple and have good-case latency 1 big delta plus 2 small delta. So if the small delta is 0 under the good case, then our protocols are optimal. However, there is still a gap between the lower bound 1 big delta and our upper bound when the small delta is not 0. And this is an interesting open problem. Finally, thanks for your attention, and I'm happy to take any questions.